Stanford University.
I'm pleased to come and talk to you here. I know there are people with very different backgrounds, so please raise your hand if I'm losing you completely, and I understand there will be questions and answers at the end, quite a bit time for that. So just in way of clarifying, I come from engineering side, power systems engineering, but over the last 5-10 years, I've been working also on relationships between the technical solutions, dependence between the operations and market designs, and now more recently, ways of integrating renewable resources and new technologies into operation. So I'll give it a try to give you a big picture about how we see what the sustainable electricity services would be and some of the open questions. So this is just an acknowledgement to the group that I lead. And I would like to start first by sort of taking a step back and saying that sustainability is not just being environmentally clean. It has many other attributes. And argue that in order to make the system become sustainable, a lot of current practices, planning and operating practices by the industry have to be revisited in the sense that we have to rely much more on just-in-time, just-in-place, and just-in-context services. And I will define that as we go. Just very briefly for people who have not followed much what's changing in from the physical side in terms of new resources, I'll give you a little bit of picture of how is the physical system changing. And then want to introduce again very briefly the idea that we are pushing at the Carnegie Mellon. We call it dynamic monitoring and decision systems. It's sort of cyber system overlaid to facilitate the operation of physical system as new technologies are being integrated to the system. And then as an example of that interdependence and interplay between information exchange and the physical operation of the system, show you how you can actually how you can integrate wind, which is very variable with demand-side response, and still have the system operate very well. And along the way, emphasize that this is not a question of designing the best technology, the best component, but is the question in which efficiencies and reliability comes from the system's interdependencies. So the first thing is just in way of clarifying, because from the engineering side, power engineers worry about the supply and demand meeting on almost instantaneous basis, and that's what engineers like to think about as a viable system. You have enough power to supply the demand every minute, or you have to have that also when major components in the system fail. If you lose the transmission line or lose a generator, supply and demand have to unconditionally meet. So this is where the engineering is. You have to make the system reliable. And in addition to that, now we have more of the efficiency measures that are expected from the system as we want to squeeze more out of the system. So, so these are the technical attributes of sustainable system. Efficiency short-term, efficiency long-term, efficiency, they are now also attributes of sustainable system, and environmental sustainability is just one piece of it. So they're all interdependent, and so we cannot make the cleanest system without worrying if it's reliable, et cetera. And also, there is a lot of worry about the technologies getting on the system, being subsidized and not recovering their costs. In other words, having the business sustainability for different technologies. So that all together in our definition forms the notion of sustainability. So in order to make such a system from where we are to what it might become, we suggest that the future system should have functionalities that the system right now doesn't have. And some of these functionalities are just-in-time actions. Just in particular, we'll talk about the value of prediction, dynamic decision-making, look-ahead decision-making, which would actually smooth out different uncertainties and so forth. And also about just-in-place, because this is a network, so you have to deliver the power to the right location. So they have to have a lot of distributed interactive information exchange and interactions between different components on the system. Just in context is a sort of fuzzy term that we have introduced, which talks about different responsibilities, different risk managements, and different costs and values that come about by these different technologies, depending on what organizational rules you have. So that altogether, these three are sort of new functionalities that one can associate with the smart grid. And in order to even begin to think about these new functionalities and their value, I would like to just very briefly summarize and sort of contrast the objectives of today's industry with the objectives of the industry the way we believe it's going. So in today's industry, the current practice, operating and planning practice, basically has the objective of minimizing total generation cost. You schedule supply, the cheapest supply, to meet given demand unconditionally, and everything else is a constraint. And this is how the software works in the electricity markets everywhere. So you provide, you schedule supply to meet given demand, but you do that so subject to predefined CO2 constraint that power plants have to meet, subject to transmission constraint. Even you can extend it even to the ideas of building storage to balance supply and demand. Doesn't matter what it costs. So it's just really a constraint. And build new transmission lines for forecast demand, independent of what the value to the system is. So from the optimization point of view, this is a large, complex system. You're optimizing one objective subject to a lot of constraints. And everything that is a constraint effectively, from the economic point of view, becomes an externality, which further becomes a public good. And if you package all these into public good and externality basket, then it's very hard to give incentives to put some of these technologies or not on the system. So instead of doing that, one way to rethink the problem is to say, OK, this new industry will be sustainable if we think about reconciling trade-offs. So this is already going on a little bit in the electricity markets when you have elastic price-responsive demand. So you schedule supply to meet demand, but there is a demand curve which values the value of electricity that customers use. So it's not unconditional supply of demand. So reliability becomes something else. Depending on how much customers want to pay, that's how, you supply them more or less. So this is the trade-off now between the cost of generation and benefits to the customers, rather than schedule supply to minimize the total generation cost subject to constraint that the demand has to be unconditionally what is given. And similarly, if you go one by one, you are going to see that it is possible to rethink any of these constraints now, to reformulate them as a trade-off thing. And by doing that, then becomes necessary to think about what is the product, actually, that we have here. So is the product, if you want clean energy with a price-elastic demand, that's a very different energy product, electricity product, than something that you just buy energy subject to typical constraints. And the question really is, sort of the hidden premise here is that if we have a mechanism, if we have an implementation of the signal exchanges and the rules on the system which actually enables reconciling these trade-offs, then the system will be much more sustainable than if you think that if you just try to do one optimization for generation cost and treat everything else as an externality. And I will try by means of example to show some of that. So in order to even begin to make the case, I want to, for people who haven't seen power grids and so forth, to very quickly show what is it now, what information exchange exists, what signals are given about the value, and which ones are not there. So this is your typical power system of today. This is the high voltage grid. This is the control center, large power plants, and very high voltage transmission lines. And then you are going down to substations. These may be entries to cities and so forth. And there are a lot of small customers, below the substation level, low, medium voltage level grid. These are what's known as distribution networks. And one thing to observe for the purposes of discussion is that the only information exchange, online information exchange that exists nowadays is the lowest maybe at the substation level. And there is no further online information exchange here with the customers, with the small customers below the subtransmission level. So it is not, consequently, it's not possible to take into account information and sort of, you can meter these customers, but you still have to communicate the information about what they want to do on the system. And we don't have that now. So consequently, the customers are basically, they're diverse, but there is no any active adaptation on the customer side in today's environment. And the dispatch is done, economic dispatch, this minimizing total generation cost is done in such a way that you just assume that the demand is whatever it is without getting the information, online information from the lower level customers, and then dispatching unconditionally or with very little elasticity may be given by the utility. And so what happens then, the basic problem of dispatch and meeting the supply and demand is the problem of the conventional approach to economic dispatch is to supply the expected inelastic load with whatever produced by intermittent resources combined with other traditional power plants. What that means, you have here expected system load. This is typically at the system level. It's fairly smooth. By the time you combine that expected load with wind generation, which is fairly fluctuating, then this is the expected net load. So now the utility has to balance this load, and it should be clear that unless you have some adaptation, these imbalances have to be balanced with some very fast resources. So one thing would be that I really need storage to deal with these spikes, and we are going to argue that you may not need necessarily storage for that. Okay, so this is how it's done now, and as part of the smart grid, as part of deploying new technologies on the system, there are some changes which actually call for rethinking how the operation should be done. So there is conceptually, everybody's talking about having meters in their house. That's presumably to have more responsive demand. You would have, there are a lot of distributed resources, PVs, PHTVs ultimately, et cetera, small wind plants, geothermal. They all come under these variable resources. And then in addition, there are new security environmental constraints, cybersecurity, and so forth. So the problem now seen by the system operator that it's much harder to predict supply and demand imbalance by the control center operators. And we are going to argue that it's going to be necessary to have this self-commitment by the distributed resources and load-serving entities in order to deal with that problem. And that there was going to be needed information exchange to actually deal with that. So again, in terms of physical picture, there are many, many more new resources here, PHTVs, fleets, large-scale wind farms, pump storage. This is how the system is physically changing. The old system was the orange and blue, and all this green stuff are new technologies added physically. And then one of the premises that I would like to put forward, that it's extremely important to think about changing that communication pattern that is offered by SCADA, today's SCADA, into something which becomes what we refer to multi-directional, multi-layered interactive IT exchange. And I will show a little bit more what that means. What that means is that there has to be some sort of information exchange online, not necessarily real time, maybe in predictive way, at some level of aggregation, that information should be communicated all the way up to the control center level so that ultimately only the conventional resources get used only to balance things that don't get balanced by the distributed resources. And that's a very different paradigm than what we have now, because we don't rely here. This is, at this level, you just predict that total load will be something. You don't include into consideration demand response or compensation, storage by PHTVs, et cetera. So in order to include that, you would have to have information exchange. And then, So two things are needed. More information exchange between different layers in the network, and also, we call them DIMOs, embedded intelligence for decision making, for sensing and control at the distributed sources. So, for example, here in the house, you have smart meter automation for appliances. That's your dynamic embedded intelligence that somehow interacts with you as a distributed load, in this case, with the rest of the system. Here, somehow, this decision how much to consume at the household level has to take into consideration that there is a solar panel or no, et cetera. This is a green factory, for example. If you have the wind power next to the factory, you would be doing one thing, or if you don't have it, you would be doing something else. So there is this automation, distributed automation embedded into users level, in the distributed resource level, which now it's embedded into different distributed resources, which in turn communicate with the system operator. And these together is an IT-enabled, sustainable, smart grid. One way of thinking about it. Are there any questions or yes?
What benefit is it to have, say, your washing machine communicate with the larger grid?
Right. Yeah, so I should clarify that. So I will get to that a little bit later, but not the smallest customer has to communicate to everybody high up. You need some way, some aggregation. You may even think about, I think Sally was talking about, sort of intermediate operators which aggregate different technologies, which in turn talk further to the higher up level. So the communication is these multi-directional arrows show what the communication is symbolically, but we are spending all of our time on actually figuring out what information should be exchanged and for what purpose. So that's the rest of the talk. I'm just introducing the concept. Thank you. Okay, so what is the potential benefits? Okay, the potential benefit is now I can have, you're familiar with this now. You can have demand response versus expensive conventional generation balancing the wind, for example. How to integrate that? What information needs to be exchanged with whom and for what, for what potential benefits? So one thing that we've been playing a lot with is that in order for this to be done in a sort of feasible way, it is not good to have distributed resources react instantaneously to the price signal. They should have some embedded intelligence which is model predictive, based on the technical characteristics and the physical constraints and comfort levels that load, for example, wants to have. They would decide how much they want to participate and cut back and create their demand curve. So prediction will smooth out the uncertainties, and that needs to be communicated to either to the aggregator or all the way to the market. And if we are arguing that there is a huge value in this prediction, and I want to go through that in some detail. So basically, the idea is instead of having the system operator dispatching everybody, also these very novel technologies that the operator doesn't have good characteristics and doesn't know much about, there would be self-dispatch, but a little bit coordinated. And so different technology would perform look-ahead decision-making, given their unique temporal and spatial characteristics. They would create the bids, which will be given either to the aggregator or higher up to the market in order to incorporate their potential either needs for power or supply of power that they would provide. So basically, if you do this, so sooner or later, this bid somehow is the information that the entity responsible for balancing supply and demand has to have, and that bid should be different for adaptive demand than for wind power plant, etc. So how to put all these pieces together decides now what information needs to be exchanged. And so I will illustrate this on an example of wind and elastic demand. Okay, but the basic technical idea, just for a minute, I hope I don't lose people too much who are not mathematical here. So the idea would be that, let's say, there is this embedded intelligence at the distributed level in which demand, for example, knows for the next 24 hours what is the predicted price of electricity, and he would have his own constraints, how fast the load can turn appliances on and off, everything in an automated way. And based on that optimization, which is look-ahead optimization, the demand would produce the bid curves and give them higher up. And similarly, the idea is that even variable resources like wind power plants could do that up to a certain level of accuracy, let's say 10 minutes ahead of time and so forth. So the more prediction there is, the more information, the more optimization at the distributed level, a self-dispatching level, the better the system works. It's more efficient. Okay, so this is the graph that I should not really be going into, but it would show what type of information exactly you would have to exchange in terms of bids, etc. So without going into the math, the net result would be that, let's say, if you're a conventional power plant, you would bid your generation supply bid. I'm willing to supply so much power between some minimum power, maximum power at that price. If I'm in elastic demand, I'm willing to pay any price and consume power that I want unconditionally. If I'm price-responsive demand, I'm willing to cut my demand if the price of electricity. I'm willing to pay a lot to be supplied my minimum power that I need. So that's very valuable to me, but I'm just going to use less, to pay less for more power. So this is typical demand curve. And these demand curves, I don't have time to go through it, but they are results of this distributed decision-making by the responsive demand or by the power plants. And an interesting one, again, that I don't have time to go into is PHTV, because they can be either, PHTVs, they can either be in the supply mode or demand mode. And so depending on, they have to create this one curve which reflects the value of them charging or discharging depending on what the projected price is, etc. So this is the information that gets sent from the bottom up to, by the distributed resources to higher up to the aggregators or further up to the system operators. Okay. And similarly, I just want to illustrate a little bit on the demand side what this means. What industry is doing now, they're doing this direct load control. That means that there is some information that utility has pre-agreed with the customers to disconnect the customers if there is shortage on the system and so forth. In other words, there is no online information exchange from, let's say, the large customer as the prices change in a predictive way. So instead of doing that, just very little math. Instead of doing that, this is what would be inside. For the anticipated price of electricity that comes from the system operator or some time horizon, which is not just single sample time, over some time horizon, the load would minimize the total cost of staying within, let's say this is a thermal load. Total cost of deviating from between the minimum and maximum temperature acceptable. And it is at this level only that load can actually take very detailed information about its characteristics, which are different than the characteristics of some other load. So this is basically saying internal temperature is changing as a function of its own temperature at some time constant. And it also is a function of how much power the house consumes. And so the decision is then, in a look-ahead way, how much to consume power so that you minimize the expected cost of staying within the constraints and paying for electricity, and it's subject to being within the limits that are acceptable. So by the time you solve this problem, you would actually create your demand function, and you would communicate it to the system operator or to the aggregator. And an interesting thing is if this is done in look-ahead way, the demand functions are different for different hours. And so the system operator just takes these static demand functions and clears the market with the software that they have now. But all the dynamics, all the sort of very specific characteristics about the technology, the demand response, and so forth, they are internalized. And if you do it that way, then you have basically this information exchange between the small users, aggregators, and the market. And there is a system because the end user has the option to actually decide how much he values and to internalize the constraints that he has rather than the market system operator telling them you are going to turn off or on when it's needed by the system. And this is again now load serving entity also can optimize its profit depending on how much it pays to the market to serve the customers and how much it's paid by the customers. So I'm not going to get into mathematics of that, but let me explain just on an example what that really means. So take a typical system. There's a generator with natural gas, coal, solar, another coal plant, wind plant. And if you don't have wind, with this typical load, system load, the total system load is very smooth. This is this blue line. If you have wind, wind is negative load. If you treat it as a negative load, this is going to be net load. And so the intertemporal constraints are very important. Gas plant can respond at certain rate to deviations. Coal can respond at different rates, etc. So this is a very important part. Depending on how is the dispatch done, you are going to have very different impact on these technologies. When are they scheduled and how much they are paid and how much they are paying, and also what is the total system cost. So the conventional dispatch basically is saying for the coal power plant, you just schedule it relatively slow, don't take advantage of the trends. And so this is a result for the coal plant. This is for the other coal plant. This is the way ISO clears it now. If I do centralized predictive dispatch, what means you are doing centralized dynamic programming, taking into consideration all the ramping rates of different technologies, then you are going to get this benchmark result. This is the best that can be done. But if you do distributed predictive dispatch, if every plant, every distributed resource optimizes in a look-ahead way its own objectives and communicates these bid curves, then you're going to have these dotted black lines, which come very close to the centralized predictive dispatch. This is to show that we can rely quite a bit on the dispatch locally without making it too complicated and coming pretty close to the best that can be done. The implications of this on being able to integrate wind are very interesting. So this is your original load. This is the green dotted line is as the wind blows and then ceases to blow, the demand right away follows, right, in a predictive way, 10 minutes ahead of time. This is the scale that we had here. So the system automatically balances in a self-adapting way. You don't have to use other resources, in particular natural gas in this case. So what you would see here is this spiky dark red line is basically how much you would have to dispatch natural gas power plant in order to deal with these deviations in wind. While if you do it in a predictive way, you are going to smooth it out and use much less of natural gas and use it, and environmental impact would be much smaller, etc. So this is what we consider proof of concept, that you can actually implement 50% wind capacity by relying on elastic demand, but with very careful self-committing dispatch and in a predictive way. Otherwise, if you just do it in a static way, the way it's done now, you know, these benefits of temporal fitting of supply and demand actually cannot be taken well into consideration. And this is, for this particular example, these are not realistic numbers. This is your demand quantity, how it would change. This is the price-responsive demand. How would it change to meet that, to compensate for wind deviations? And this is the elasticity, how much it changes. Again, very hypothetical numbers. We don't have real numbers. And potential savings at the system-wide level are significant. So this is the difference between the cost that you have if you don't have. This is inelastic demand. This is total cost. And with the elastic demand is 0. So savings could be quite significant. Just one more thing, and I will stop. And that is, you can think about PHTVs. You can think about any technology this way. So if you have PHTVs, fleet of PHTVs that sees the predictive price of electricity, they can adjust, internalize how much are they going to need to charge and discharge in anticipation for that price, and this is how much they are going to go to add to the total electric load. The point being that the peak load is not going to change much at all. If you actually do just this fast charging whenever you need and you're in an open loop, then the load, system load, electric load, is going to grow in a very significant way, and that's what utilities worry about. That means you may have to build 2 large new power plants, and so the trade-offs begin to be very, very shaky. And for us, you know, from the systems point of view, this is really just the question of what embedded automation, the decision-making you have to put at the level of PHTVs, what it needs to be exchanged in anticipation with the price curve, et cetera, and what information needs to be given from the ISO down or from the aggregator, depending on the level of aggregation. So the point is that without that information exchange, you have this result, and you have to build much more. With the information exchange, you have this result. And so it's much more sustainable. You meet the same objectives with much less resources and a higher utilization. OK, so I think I ran out of time. There is another part which questions how much you bundle environmental signals with energy signals, with congestion, et cetera. I'm not going to talk about that, but just want to stop by saying that there are a lot of open questions here, depending on how do you treat the electric energy as a multi-product or a single product in which everything is bundled? How much do you aggregate? Do you have these intermediary aggregators? The outcomes are quite different. But one point is quite clear that based on these initial simulations, that without these predictions and interactive information exchange, you're going to basically add these new technologies which are very variable and have to build much more of conventional technologies and reserves to deal with them, and then the economics are completely gone. So this is all I wanted to say. I'll stop here. There are more slides, but I will. If you have some questions, I'll be happy to answer. Thank you. Yeah, thank you.
Okay, so questions. Okay, how about starting back at, you. Yes.
So on the topic you talked about a given system that operated within a constraint, that it would you spoke of temperature constraint. You said that it would use the price signal to decide how much power to extract that.
Right.
So I'm envisioning a situation where we have a lot of those systems, and they're all acting on the same price signal, and so we're expecting like a peak load condition, so they all start to ramp down their power usage, and then it turns out that maybe we don't need some peaking plants that we thought we would need in that hour. And so then the price of electricity that we expected to see is then much lower. Do you include that in the model? Or?
Yes, absolutely. This is this iterative interaction. That is the whole idea. That unless you take that feedback, the effect of adaptation, then you're doing it open loop, and then the price, you're just price taker. But here you are no longer just a price taker.
Would this kind of dynamic optimization require a deregulated electricity market, or could it be done in a regulated market? Because a lot of the variable renewables in the West where there aren't necessarily deregulated markets.
I really don't think that this is unique, that it has to do anything with deregulation necessarily. The question is what information you need to exchange as you do your dispatch, and who gets paid what. So I don't know exactly how to define the deregulation in context of that. I think in the limit they should converge. And so even the restructuring issue becomes smooth here. Yeah.
Okay,
Yes.
all the way in the back.
Sorry.
So for this information transaction network, what kind of communication standards and infrastructure are you proposing? And how do you ensure grid reliability and security?
Okay, so ensuring grid reliability is that supply and demand match almost instantaneously. So we do that by this information exchange, So the clearing is done based on what people want to be cleared. And at the ISO level, it's balanced so that there is enough supply and demand to balance. Security and the privacy issues we haven't looked much into, but how to actually implement this so that you have some protection against people knowing more about what your load looks, etc. There are a lot of people at CMU who are working on that. That's not my area, but potentially I think it's a doable problem.
So is this technology in trials, say, for an existing system operator? Are they trying it? I mean, before wind and solar come online, why couldn't you apply this technology and see real savings in the margin between supply and demand? I mean, if you look in California, we generate a whole lot more gigawatts than we use every day.
So I've been talking to some, friends in the utility operators, and the immediate reaction that I had to when I was presenting this, they said, well, this is sort of resembles Australian market, in which you have self-dispatch and people are actually doing that. And there's a lot of benefits from forward contracts, being, managing uncertainties in a look-ahead way. So people are open, some operators are open to trying this, but I think we are at the stage now that we should just do simulations to show more and more, what this means in terms of real numbers and so forth before we go and implement it. I should mention that FERC has a sort of begun to pay big attention to this diamonds idea, and they think it's a good idea. I don't know. It's going to take ultimately utilities to try, the industry. And I agree with you completely. This is not unique even to the technology. There is a lot of efficiency that can be squeezed out even with the current technologies.
Do you have any thoughts on how you get consumers and small businesses to provide these demand curves to you, particularly given that many of us never even figured out how to program their VCRs?
Yes. So I was this morning at a company, I can't tell you the name, they're supporting one of the students on this adaptive load management. So basically there is a business to be made here in terms of also aggregating a lot of small guys. And so, I mean, depending on how much you aggregate, you're going to get different, suboptimalities. But there is the optimization at the aggregator level would be that you have very simple contractual agreements with the customers. They deploy these technologies which are responsive in real time, but then the aggregator would go on the market and take advantage of speculations and predicting things right and so forth. So the objective for these aggregators would be to actually make the market and begin to compete with the utilities which have flat rates and so forth. Yes, yes, yes. But I guess the problem is that if you go and look into really nitty-gritty details of how the signals are being produced now in the market, even in the market, they don't reflect the value of rate of response, which is one of the key values if you want to make it sustainable. And so we were talking with Frank, he's somewhere there in the back, that you sort of have to revisit the ancillary service market design for this to work. And so there's a huge risk even for Enernox. They're doing cherry picking now, but if you really want to have large penetration, it would sooner or later have to be sustainable financially. And in the same way as with storage technologies, with everything, is it going to recover the cost in the long run? Right now, it's maybe subsidized, et cetera. I think the point is that if you do this, if you design this right, and even communicate the value of the uncertainties over different time horizons, then there is a value in aggregation also. So it's not my grandmother doing it. She won't do it.
How about over there? You had a question?
Yes, okay.
All right. Okay, how about you in the red sweater?
Yeah.
So related to that, I just am getting really worried about people gaming the system like crazy because this is really, really complicated, and yet, small businesses will have to make a decision. They're going to have to make at least a simple contract, and and then their technologies, I guess, are going to be making decisions about what they're going to bid, and then also the other part of it is like the PHTV. Well, there's a real person driving that. I mean, the PHTV has to be plugged in order to communicate at all. And so anyway, it just seems like there's some major behavioral issues that are going to have to be.
Yes, I agree 100% behavioral issues. We haven't even looked into them, but I've gotten that comment before. The only comment I have, it's really not complicated at all because the complexity gets managed at aggregation level. The markets are beginning to already work in that direction. It's just that I think it's getting the signal straight on what is the value of just in time and just in place.
You had batteries, grid batteries plugged in different places on the grid. I'm wondering if this system can be used in a predictive or simulation way to say how much battery do you need? Do you need 10% of wind or 5% of wind or 50% of wind? And what works out to really save money?
You mean for at the planning stage? Yes, yes. We have a PhD student who is almost done. She's doing, it's a very difficult subject. How do you plan with these different technologies? Because you have to do the planning horizon, it's sort of dynamic programming under uncertainties, different combinations, taking into consideration that it's really at that hour that there is a value. So it can be done, and we have some first examples on that. So there are two questions. One is how do you plan it at the system level? The other one, how do you plan as a technology? And I think both. So instead of having these short-run bids, you actually end up having long-run marginal bids using sort of peak load pricing idea, distributed peak load pricing idea. And it can be done for the part that is difficult is that you really need some long-run demand curves. And that is where you would have to ask Public Utility Commission to say, okay, customers should tell me what they need for the next 3 years, how much they're willing to pay for me to plan this. So the long-run forward curve for demand is very hard.
All right, how about back over there, and then we'll come over to you.
On the speed of the optimization, is that something you do every hour, or it seems like at that kind of level that's something that would computation would take a long time and require a huge computing resource?
I'm really glad that you're asking that question. So if that centralized dynamic programming, if the operator is to do that, that's an undoable problem if you take into consideration nitty-gritty details of every household. However, if the bids are created, let's say they can be created 10 minutes, it's like a moving horizon. You optimize for the next 24 hours. So you can do that. It's one decision variable. How much do I schedule subject to my constraints? So it's like parallel processing. Everybody is optimizing their own, converting into static information, which system operator clears without temporal constraints. So it's very doable, maybe even down to 5 minutes time horizon. So we have, I could talk with you more about this, but it is very different than optimizing at the centralized level, the way we are trying to do it now.
Looking at the diagram, you've got centralized control at the top, and then you have this complete solution right down to your toaster. Does it not make some even just from an experience perspective, to go one step down in the distribution, get that sorted out, and you may find that you get 75% of what you need at that point?
Yes, absolutely.
And then,
yes.
I've lived in places where they actually have some of this demand control already in place for water heaters and stuff like that, and they have a little device, and if the peak goes up, they just send a signal out, and they say, okay, your water heater and your dryer doesn't go on.
Yes.
And it's just a signal, one little thing they send across the
So it's an interesting thing. You have to have some aggregation. You'll never go down to the smallest guy. The more aggregation you have over time and space, the less optimal you are with respect to some benchmark. But on the other hand, what is true is that you don't actually do this as a direct control. Right now, you have direct load control. I say, I am willing to take a cut of, I'll pay 2 cents less, and you can cut me so many times a year. That's very different than what we are talking about here. And so maybe there are examples of distribution systems doing this, but they're all applying direct control rather than adaptive.
What do you think the perspective of an investor who is considering to invest in a system like this should be?
Funny you asked. I have a startup company, and investors are looking into that. Yeah, I think it's risky in some sense, because it depends on, in order to implement this, you have to have some regulatory changes and support. So one of the reading papers that I sent was in the Public Utility Fortnightly. We say that you really have to have rules, rights, and responsibilities which enforce this information exchange. It's binding. If it's not binding, then the risk is high, because people are just going to say, and they are going to do something, and they don't do it. So the risk comes from there, but actually I think it opens the door. It would open the door to a lot of new technologies that they sort of come to the right place and they have the right value. So investments into the new technologies, I think, would be very good if you had something like this.
Two-part question. You mentioned, on your slide, you mentioned an IEEE paper, working paper, 2009. Is that published?
Yeah, most of them have become actual papers. So I'll tell you, I don't know exactly which one, but they are published. Most of them that I refer to are already accepted and published.
Okay. RTS system, EESG?
Oh, no, that is most of them are published, yes.
The other question is, about 2 years ago, Dr. Willett Kempton from University of Delaware was here, spoke at this energy seminar. And I believe he's working with the RTO in Greater Delaware, Maryland, Pennsylvania area. I think it's called PJM.
Yes.
They are doing some modeling now with banks of PHTVs and have minimum capacities of a megawatt. And I believe the utilities won't talk to you below that level. Right. Is that about the threshold where the centralized control would go down to local blotches of megawatt power plants?
Yeah, I think it has to, because you have to aggregate at least that much in order to, and so this is the question of design of the market and how much. Utilities are large now, so they're huge aggregators. Can you make them smaller? How much smaller? And what are the implications of that? But right now, I think the rules are too restrictive, too large.
So conceivably, if I have a huge photovoltaic array and a car in the parking lot all hooked up, I could supply my neighbor when he turns on his hot tub at the middle of the peak afternoon, right? So it would be, all the control and distribution would be done at a truly local level.
Right. I think it's a lot of stuff is distributed. Maybe just show this one very quickly. So when I gave version of this like a couple of years ago at Caltech, John Doyle said, well, can you actually do completely plug and play without information exchange with the others? And what you get if you do that, you have these oscillations. It takes a long time to discover the information that you need, what are the... So it is very good to have signal which comes from the system coordinator, anticipated signal, and that speeds up the process of converging. So plug and play, completely distributed, very likely, because of the temporal constraints, is not going to work, because this would cause too much frequency deviations on the system and so forth.
Two quick questions. One is, would any of this work in microgrid, campus type environments?
So we are talking...
Would any of this apply to water or the systems other than that? First, the microgrid.
Okay, so the microgrid, again, I don't know if we are talking about a test bed on an island, which would be a microgrid to try this. And I think it's fairly serious, yeah, absolutely, yes. And actually, on the smaller system, you show, that if you don't do it, then consequences, you have much more oscillations and things go either too expensive or reliability is lost. On water, I don't know. My wild guess is it's another system with supply and demand and delivery. It should be applicable. Time constants are very likely very different, etc. So I haven't looked into water, but why not?
In some ways with water, there are already aggregators. The water districts are in a sense an aggregator. So they're just a random thought. Anyway, more questions. Okay. What's one more? Yes,
just to build on the gentleman's question up front, is that if you wanted to, as an aggregator of electric cars, bid into a contract, say of a megawatt of people with cars, that wanted to buy, say, 50% wind energy, could you not build into a storage infrastructure and have that storage filled with wind whenever it came, so that you're managing electricity like we manage water?
Yes.
We drain reservoirs when we know a storm is coming, we put it in percolation ponds fairly predictably, and nothing overflows.
Absolutely. Yeah. I forgot who was telling me that it's very real that the wind plants being built close to the hydro reservoirs, and that's a very good...
Or do they even need to be built that close? If you know that you need to fill a reservoir, you're just creating a very large load on the network, and you can fill it 6 hours ahead.
Right.
You need to have it drained, because as the Danes found out, more wind and storage.
So I agree 100% with the concept. The thing that I always ask my students when I say, who are you? If you are, virtual power plant, you have one objective, and all these pieces somehow have to be integrated so that the system comes together, and you have to have the right, incentive and signal sent back for what you are doing. And that's the missing piece, I think. Yeah, but technologically, yes, and it makes a lot of sense even economically. Yeah, I think there is one.
Okay, we'll have one last one, and then we'll be done.
Well, you had a slide on the overall simulation where you were trying to figure out the cost savings for system-wide.
Right.
I didn't see a metric for an example cost. Did you ever run a full system simulation and figure out a percentage cost saving?
Yeah, this is exactly what that was supposed to show, that you have this simple system, we call it RTS system, that engineers like to test reliability on. It's a hypothetical system, but it's supposed to reflect some real-world system, in terms of electrical distances. And so you have a typical generation mix. Now you replace portion of generation mix with wind, right? So there are several things. If you didn't replace it with wind, this is the total cost. I have inelastic demand, etc. Then I replace it with wind without predictions. I get a total cost. And that savings that I showed was the difference between if you have predictive, adjustments, as you were describing, versus if you just use, if you balance wind as a negative load. And I should say one major thing here that was not done. This is only for look ahead. We didn't account for reserves at all. So there is a very major thing, very major gain here, that if you do it the way we are proposing, you're going to need much less reserve because the spikes are not that high. like what I showed with the PHTV. So the savings are shown are just the short-run savings.
So without wind, if you just do without wind with elastic and inelastic, what was the approximate net savings?
I think I would hate to go into numbers because it's very system dependent, but and we don't have the real, elastic demand, etc. So I think the next step is also to see what this means in terms of some real systems. But this is just to show the proof of concept that it's actually doable, and I think it's for the first time shown that with very little, distributed optimization and the right information exchange, you can go much further in terms of squeezing the efficiency and staying reliable.
Okay, all right, well, thank you very much.
Thank you.
For more, please visit us at stanford.edu.